Hello students. In the last video, we have learnt about deforming force and restoring force. So what is deforming force? It is the external force which is applied to change the shape and size of the body. And what is this restoring force? When deforming force is applied to change the shape and size of the body, there is a force which is acting in opposite direction to restore its original shape and size. So it is called restoring force. Even we have learnt about stress, strain, then Hooke's law. So what is Hooke's law? Stress is directly proportional to strain within elastic limit. Then three elastic constants we have learnt. Those are three elastic moduli. First one, Young's modulus, then shear modulus, and third one, bulk modulus. So what is Young's modulus? It is the ratio of longitudinal stress to longitudinal strain within elastic limit. Then shear modulus is, it is ratio of tangential stress to tangential strain within elastic limit. Then third one is, that is bulk modulus. It is the ratio of volume stress to volume strain within elastic limit. Today let us see next part of it, that is stress strain curve. So what is this stress strain curve? Definitely it is a curve drawn between stress and strain. Means it is a graphical representation of stress versus strain. Now let us see, generally we used to take this type of graph. Along x-axis strain is taken and along y-axis stress is represented. It is the most common curve for maximum materials. Now let us try to understand this graph. So many points are marked here. So let us try to understand. The stress strain graph has different points or regions as follows. First one, that is proportional limit. Second one, elastic limit. Then yield point, ultimate stress point, then fracture or breaking point. So what all these, let us try to understand. So if you observe this graph, this O to A, you observe this graph O to A, it is a straight line. Straight line means what? Definitely stress is directly proportional to strain, means the material obeys Hooke's law, means it is more elastic in nature. So this O to A represents, it is a straight line, it represents Hooke's law is obeyed at this part, so the material behaves as elastic body, means it regains its original shape and size after the removal of deforming force. Then, now observe this A to B. This A to B, it is not a straight line, means it is non-uniform curve. Stress is not proportional to strain, but at this part still the properties of elastic body are remaining, means at this part still some part of elasticity is remaining for the respective material. So this point B in the graph, it is called yield point or elastic limit. So what is this elastic limit or yield point then? It is the point till this material will maintain elastic property. Okay. So O to A, stress is directly proportional to strain, so it is proportional limit. Then B is, this is elastic limit, or say, you can say it is yield point. Now if you observe the graph from say point C to D, or even from point B to D you can observe. From B to D, stress, it is little increase in the value of stress, but observe this strain now, it is more. Means what? This strain increases rapidly from point B to D. Then at the point D, if you observe, this point D, we used to call it as ultimate stress point. So what is this ultimate stress point then? Here very less variation of stress, only this much of variation in the stress. But observe the strain here, variation of strain is more. Means at some point, even you can say stress can be 0, but strain cannot be 0 here. Okay, so at this point here, this point D, it is ultimate stress point. Then if you observe this one, very less variation in the stress but more variation in the strain, means now material is exhibiting plastic behavior. Means the material continues to elongate even for small increase in stress. So here in this region, that is B to D, Hooke's law is not applicable, it is not obeyed. Okay, so this is ultimate stress point. Then definitely we can observe the next curve here, means next segment you can say, that is D to E. If you observe, here stress is decreasing but strain is still, it is increasing. So stress decreases but strain is increasing. So this part of the curve indicates fracture. Means if wire or a material is elongated, then definitely that material will break. So it is called breaking point of the respective material. This part, that is D to E, it is very important to identify the characteristic of a material. Characteristic of a material means you can say whether the material is brittle. Brittle means very hard, or whether the metal is soft. We can identify only by seeing this part of the graph. If this point E is near to D, then breaking point is very near to D, means what? Easily you can break that material, means definitely that material is very hard in nature. If this point E is little far from D, okay, then the respective material is soft in its nature. So this stress strain curve helps us to identify the characteristic of a material. I hope you understood this graph. So let us revise it once again. From O to A, stress is directly proportional to strain, means Hooke's law is obeyed. Material behaves as elastic material. Then A to B, still some elastic properties remaining in the respective material, but stress is not directly proportional to strain. Then this point B is called yield point or elastic limit, you can say. So it is a point. After this, the material will not regain its original shape and size. It behaves as plastic. Then this B to D, variation of stress is very less, but strain is rapidly increasing. And this point D means at this part, stress is not at all proportional to strain, means what? Material has lost its elastic property, so it is behaving like, or it exhibits only plastic behavior. Then this point D is called ultimate stress point. After D, the respective material starts losing its property. So now it starts breaking. So it is called breaking point or fracture point. So what is the use of this stress strain curve? We can identify the characteristic of a material, whether it is hard or soft. So proportional limit means it is the region in the stress strain curve that obeys Hooke's law. In this limit, the ratio of stress and strain gives us proportionality constant known as Young's modulus, and the point OA in the graph is called proportional limit. The next one is elastic limit. It is the point in the graph up to which the material returns to its original position when the load acting on it is completely removed. Beyond this limit, the material doesn't return to its original position. Then yield point. Yield point is defined as the point at which the material starts to deform plastically. After the yield point is passed, permanent plastic deformation occurs. In the graph, point B represents yield point. Then ultimate stress point is a point that represents the maximum stress that a material can endure before failure. Beyond this point, failure occurs. That is from point C to D. Then fracture or breaking point. It is the point in the stress strain curve at which the failure of the material takes place. That is from point D to E. Okay, so this is stress strain curve. Now let us take next one, that is expression for Young's modulus in the case of stretched string. Let us consider a wire of length L and is suspended to the rigid support. Say this is wire and this is rigid support. Length of the wire up to this point, it is L. Let A be the cross-sectional area. Then let us apply some mass here, attach some mass. So when we attach mass here, what happens? This wire gets extended. So let this dl be the change in the length after attaching the mass. Then as we know, this one Young's modulus is represented by the letter Y, and this can be written as longitudinal stress divided by longitudinal strain. Then longitudinal stress can be written as force divided by area. Then strain is change in length divided by original length. So formula will be Y is equal to F divided by A whole divided by DL divided by L. Now adjust the terms, shift it to numerator. You will get Y is equal to FL divided by A into DL. This is formula to calculate Young's modulus. Say the given wire is cylindrical in nature. Then area can be calculated using the formula pi r square. Here pi is not typed properly, so displayed properly. So I have written A is equal to pi r square here. For cylindrical wire, A is pi r square. So the formula to calculate Young's modulus is, or expression for Young's modulus in case of stretched string is, Y is equal to FL divided by pi r square into DL. F is force applied, L is length of the wire, then R is radius of the wire, and DL is changed length of the wire. So this mechanical properties of solids, it is a very small chapter, and you can understand it very easily because simple points are covered in this chapter. So this completes mechanical properties of solids. Thank you.